Hello my dear friends, I am Shubham from LearnoHub, the free learning platform where you can study physics, chemistry, maths, biology absolutely for free at learnohub.com. So then, let's start. So friends, as you all know today what we are going to learn, your class 10th ICSE chemistry chapter number 1, periodic properties and variations in the properties, physical and chemical. But let me tell you an interesting thing that throughout this entire video, we are not only going to learn the concepts of this chapter, but we are also going to solve some questions at the end. Okay, so then quickly let's start without wasting much time and let's rock. So before moving ahead, let's first see what all things we are going to study in this entire video. Okay, so first of all, we are going to see why we are going to study this chapter. Very important question and very necessary also, right? Then introduction, and in this introduction, we are going to quickly go through the very much interesting story of the development of periodic table. And then you guessed right, we are going to study about our modern periodic table, which means that we are going to see in detail about the periods and the groups of the modern periodic table. Okay, then we are going to see the variation of number of shells across the period, down the group, and the same variation of valency across the period and down the group. Okay, no need to worry about it right now. We are going to just start, and throughout this entire lecture you would feel very much enjoying, because we are going to follow the sequence and we are going to follow the pattern in which we are going to study these things. Okay, so, and lastly, we are going to solve some. So, before starting to learn this chapter, let's move on to the first and the foremost question which should arise in every student's mind before learning any chapter in this world, and that is why to study that particular chapter. So now, in this chapter, we are going to study the periodic table in detail, as well as the periodic properties and their variations. So, why on this earth now we are going to study this, or why should we study this chapter, right? So now let me tell you an interesting application so that you would feel interested and enthusiastic to learn this chapter. So very common element which behind which entire world seems to be running like mad. Okay, and yeah, it's pretty precious as well and costly as well, and you know it is, you can see in the screen, it's gold. Yeah, so entire world keep the track of this element every damn single day, how much the value price varies, and we all know why we use this element to make jewelries, right? Because it's inert, right? Because it doesn't react readily. We can see with our own eyes that gold doesn't perishes readily. But do you know the exact chemistry or exact science behind the inertness of the gold? Can you explain it? No? Yes. And like this, there are thousands of such questions which you could discover if you would study this periodic properties and their variations. Okay. Now, that questions or this question too is quite complicated for you to understand at this level, but for understanding the depthness or the detailness of the answer or the reason or the science or the chemistry behind the question, you should first study the basics of this periodic property, and that basics, like your ABCD, lies in this chapter. Okay, after studying this basics, you would go and study the advanced things, and then you would definitely answer the question why actually gold is inert, and like so many questions of other elements as well. So feeling interested and feeling convinced? So let's start. So let's start with the introduction, and in this introduction, we are going to have a very quick recap of the story of classification of elements which you have already studied in your 9th grade, right? So in this recap, we would have the scientists as the central figure, and we would revise it in the way that what the particular scientist contributed towards the present form of the periodic table. Okay, so starting with the Dobrenner, as he was the first, what he did is actually he took or he grouped the elements in group of 3, okay, which is also called as a triad, and these elements were having similar physical and chemical properties. Okay, so now let's take an example. Here, Dobrenner grouped lithium, sodium and potassium. He found that these elements were having similar physical and chemical properties, and then next thing he noticed is the middle element of this triad. Okay, now in this case it is sodium. It has the atomic weight which is the arithmetic mean of the other 2 elements. Okay, and also this middle element also has the properties which were intermediate of the other 2 elements. Okay, so like this, like lithium, sodium, potassium. The another triad is calcium, strontium, barium. You also have to remember the atomic weights as well. Okay, in this case, lithium has 7 and potassium has 39. So if you would find the arithmetic mean exactly, you would get 23 of sodium. Okay, so now in this case also, calcium has 40 atomic weight, barium has 137, and if you calculate the arithmetic mean, you would get strontium's atomic weight not exactly 88, like more than 88, but the atomic weight of strontium is 88. So approximately the arithmetic mean of the calcium and barium is the strontium. Okay, and moving towards the chlorine, bromine and iodine also, here the bromine's atomic weight is also approximately the arithmetic mean of the other two elements. Okay, and the strontium and the bromine's properties, Dobrener found that they were intermediate of the other two elements. Moving to Newland, what he did is actually simply he arranged the elements in the increasing order of their atomic weight. Okay, just like you see in this table. And then he noticed that starting from any element, okay, just like I'm starting from beryllium. Okay, the 8th element, so if we would count, we would find that 8th element is magnesium. This 8th element, he found that has the similar properties, both physical and chemical, to that of the first element. Okay, so here we go. Next is Mendeleev, and yes, this is the hero of our story of development of periodic table, because he was the first one to give us the first periodic table of elements, okay, named after him, Mendeleev's periodic table, and he was also the first one to give us the first periodic law, named after him, simply Mendeleev's periodic law. Okay, now we are first going to see how he arranged the elements in his periodic table, and then we are going to see in the next part of our story that how he gave his law. Okay, so Mendeleev arranged the elements in increasing order of their atomic weights, okay, in horizontal rows. So you can see here the horizontal rows. See here, it is row 1, okay, it only has hydrogen. In the similar way, row 2, okay, it has elements. Then row 3, row 4, 5, 6 and so on. Okay, and he called this horizontal rows as series. Okay, and arrange the elements in vertical columns as well. Just like horizontal rows, he arranged the elements in vertical columns as well. So you can see here the column number 1, column number 2, column number 3, column number 4 and so on. Okay, and he called these vertical columns as groups. Okay, just like that. That's it. No, he did a very important thing after that. He just made sure that all the elements having similar physical and chemical properties should be placed in the same vertical column or same group. So what he actually did is, just let's try to understand. Okay, if I am Mendeleev and I'm starting from lithium, okay, suppose, okay, I'm not Mendeleev, but suppose. So after lithium, I have the element which is having higher atomic mass, which is beryllium. So I just placed, after lithium, I just placed beryllium. In the same way, I placed boron, which has more higher atomic mass, then carbon, then nitrogen, then oxygen, and then fluorine. So I reached till fluorine. Now, what I would do is, next element I know is sodium, okay, which is having higher atomic mass than fluorine. But at the same time, I know that sodium has the property similar to that of the lithium. So what I would do is, I won't place sodium here. I'm going to place sodium right below lithium. Okay. Now, in the similar way, after sodium, the higher atomic weight element is magnesium. But then I again get to know from the experimental data that magnesium has the property similar to that of the beryllium. So what I do? I again place magnesium below beryllium. And in the same way, the next higher atomic weight element is aluminium. And again I find that aluminium has properties similar to that of the boron. So I placed it below boron. And the story goes on. Silicon, phosphorus, sulfur, chlorine. Okay. Now after chlorine, again I know the next higher atomic weight element is potassium. But I won't place it here. Okay. Because what is the third thing which I told you how he placed the elements? He just made sure that the elements having same properties should be in the same vertical column or same group. So I would just pull the potassium from there and bring that potassium right below sodium, and the story continues like this way. Okay, so in this way Mendeleev created the periodic table. Okay, now let's see how from his periodic table he derived his periodic law. Okay, so now first let's see what Mendeleev's periodic law is actually. The properties of elements are periodic functions of their atomic weights. Now, this statement actually seems to be very confusing, or let's make it very simple to understand. Okay, I would just replace this periodic function term by this entire phrase. Okay, now let's try to read it again so that we would easily understand what actually Mendeleev wants to tell us. So Mendeleev wants to tell us that the properties of elements are found to be similar, okay, after particular interval of their atomic weights. Now, I think you would understand right now in a more simpler way, okay, when we would see again the periodic table. Now, let's see what he says, how he determined this law from his periodic table. What I told you, the third thing, which was the most important thing, that he arranged the elements which were having similar properties in the same vertical column or same group. So, what he observed is, see, after lithium, he went till fluorine, and then again he placed sodium below lithium. So, after lithium, after particular interval of atomic weight, he found an element having similar property to that of the lithium. Same way, after sodium and after particular interval of atomic weight, okay, after sodium, after a particular interval of atomic weight, he again found an element which has similar properties to that of the sodium and lithium, that is the potassium. Okay, and same way, he found rubidium, which also has similar properties to potassium, sodium, lithium, and then again cesium. Okay, so now this story continues for all other groups as well. So what he observed is, yes, the properties of the elements are found to be similar, right? Found to be similar after a particular interval of atomic weight. And now you can see the statement. Understood? Okay, now Mendeleev just didn't classify the elements which were known at that time, but he did a very fantastic job by predicting the elements which were not yet discovered. Oh, this is a very great thing, right? Because predicting anything which is not yet discovered that it would be like that, it's very difficult. And not only just predicted the elements, but he also predicted some of their physical properties as well. Okay. Now, he also left some spaces in his periodic table so that whenever the element would be discovered, we could conveniently place that element in the periodic table. Okay. Now, you would be eager to know which elements Mendeleev predicted, right? So, Mendeleev predicted gallium and germanium. Okay. So, he called gallium as Eka aluminium. Okay. I won't write aluminium spelling. And then Eka silicon. Okay. Now, why he called it as Eka aluminium? Because he left a space below aluminium. You can see here. This is aluminium. So, he left a space below aluminium here. Okay. Now, don't worry. How are you able to see the gallium? I will tell you later. Just focus on this thing right now. Okay. Then why he named germanium as Eka silicon? Because he just left a blank space below silicon. Okay. Now, you would be having a question that how come the gallium and germanium are being seen in this periodic table? Because this is not the periodic table which was directly published by the Mendeleev, okay, right after his discovery. Okay, it's the modified version of Mendeleev's periodic table which was published at 1905. Okay, so till that time, gallium and germanium were discovered, and whatever physical properties he had predicted about them were found very close. Okay, they were having very similar resemblance, okay, to the predicted properties. The actual properties were very similar to that of the predicted properties, and this quantitative prediction of Mendeleev made Mendeleev absolutely famous, and his periodic table as well, absolutely famous. Okay, now enough with the praise for Mendeleev and Mendeleev's periodic table. Now it's time to move to see the limitations of Mendeleev's periodic table. Okay, so first limitation was what he started with, right? He started arranging the elements in the increasing order of the atomic weights, but in some cases he just ignored this increasing order of the atomic weights. Okay, now why so? Let's see, and in which cases we are going to see the example. So first one is cobalt and nickel. Okay, so let's have a look over cobalt. Here it is, and this is nickel. Now how he violated his first rule? See, cobalt has 58.9 atomic weight and nickel has 58.7 atomic weight. Okay, now you can see here clearly that cobalt is having higher atomic weight than nickel. So it should be placed after nickel. But Mendeleev didn't do so, right? Because he wanted to place the cobalt and he wanted to place cobalt along with rhodium and iridium, okay? Because they were having similar properties, right? You would be remembering the second principle of classification of Mendeleev's periodic table. And in the same way, he also wanted nickel to be placed along with palladium and platinum, okay, because they were also having similar properties. So in this case, he just overlooked his first criteria and then stuck upon his second criteria of classification, okay. Now, similar way, the next example is tellurium and iodine, okay. In this case as well, see, tellurium has 127.6 atomic weight and iodine has 126.9 atomic weight. So it's very pretty clear that tellurium is having higher atomic weight, so it should be after iodine. But actually, tellurium is before iodine. Now, why so? Same reason. Mendeleev wanted iodine to be placed along with bromine, chlorine, and fluorine because they were having similar properties. Okay. Now, this ignorance of his first criteria was his first limitation. Now, next, couldn't explain the positions of isotopes. Now, actually, isotopes were discovered a lot later than the publishing of Mendeleev's periodic table, but still, when isotopes were discovered, we couldn't place them in the Mendeleev's periodic table. Now, why so? See, first, let's understand what isotopes are. So, these are the atoms of same elements having same atomic number but different atomic weights. Okay, so let's see an example so it would be clear for you. Okay, let's take carbon, right? This element is very notorious. You would learn about it, but let's first see about its isotopes. So this is 12C6, 13C6 carbon atom and 14C6 carbon atom. These are the three carbon atoms. Okay, now you could see here these are having same atomic numbers but different atomic masses, right? So these are called as isotopes. Now, when we discovered these isotopes, what was the actual problem? See, since they are atoms of same element, so we thought that we should place them or we should give them a single position, correct? But by seeing their different atomic weights, now we again have a thought that, oh, maybe it should be given different positions, right? It cannot be given a single position. Now, this confusion or this ambiguity couldn't be explained. So that's why we couldn't place isotopes successfully we couldn't give a position to isotopes in Mendeleev's periodic table. Okay. Now, moving ahead, lanthanoids and actinoids, Mendeleev's periodic table also couldn't explain the positions of lanthanoids as well as actinoids. Now, I hope you know about lanthanoids and actinoids, but if at all you don't know, we are going to learn about it in detail in the next slides, okay, when we are going to study modern periodic table in detail. So, for now, I hope you have understood all the limitations. Now, a question arises in your mind. It should arise. So, what to do to solve the limitations of Mendeleev's periodic table? The answer is very simple, and you're definitely going to get to know this in a couple of minutes. And the answer of your question is given by our second hero of our story. Yes, our story has second hero, and he is Henry Moseley. Yes, he gave us modern periodic table, and the principle which he followed for classification of element, okay, solved the problems of Mendeleev's periodic table. Now, what he actually did is very simple. He arranged the elements in the increasing order of their atomic number. Now, what else he did to arrange the elements or to make the modern periodic table, we are going to see it in much more detail later on. But let's first focus on our answer, right? Because this is the thing which changed the entire way of classification of elements. Okay, how using increasing order of the atomic number completely eradicated all the limitations of Mendeleev's periodic table. Let's see. So, first limitation was cobalt and nickel's position and as well as tellurium and iodine's position, correct? So, here we can see that cobalt is conveniently placed before nickel. Because cobalt is having 27 atomic number and nickel is having 28 atomic number. So yes, we are absolutely following the increasing order of the atomic number, and we are placing cobalt and nickel along with the respective elements which are having similar properties to that of the cobalt and similar properties to that of the nickel. Okay, and in the same way, here tellurium and iodine comes, and tellurium is also here placed very much conveniently before iodine, because tellurium has 52 atomic number and iodine has 53 atomic number. So absolutely it would be before iodine. And here see, iodine is very happy, looking very happy, right? Because he is with bromine, chlorine and fluorine. Okay, so problem solved. Second problem was isotopes, right? So we know what are isotopes now. The atoms of same element having same atomic number but different atomic weights, right? Now here, when we are classifying the elements in the increasing order of the atomic number, the problem is actually solved, because since they are having same atomic number, it's very clear that it should have same position, and since all these atoms are of same element, it's absolutely fine. It's absolutely clear that we have to give them same position. So we actually give same position. That's it. So no more questions or no more problems for giving the position to isotopes, right? Now, moving ahead, the third one was lanthanoids and actinoids. So by arranging the elements in increasing order of the atomic number, their position also we could justify very easily. Okay. Now, let's move ahead. We have seen so far the limitations of Mendeleev's periodic table and how we solved it, who solved it, and who brought a revolution. Now, let's see the modern periodic law which Moseley gave. Okay, and let's try to understand it. So, physical and chemical properties of elements are periodic functions of their atomic numbers. Now, I am definitely sure that you would have right now figured that yes, the change in Mendeleev's periodic law and modern periodic law is just a simple term. In place of atomic weight, Moseley has used atomic number term, okay, and given the modern periodic law. Okay, now let's try to understand it in a more simpler way. Just what you have to do is, you actually know, replace the periodic function term by this entire phrase, okay, found to be similar after a particular interval, and then it would be easy for you to understand it. Now, what it states, physical and chemical properties of elements are found to be similar after a particular interval of their atomic numbers. Okay, now this seems quite simple, right? And now let's try to understand this entire statement, what actually Moseley wants to tell us. Okay, now when Moseley arranged the elements in the modern periodic table, just like in the same way we are going to, the same way Mendeleev arranged the elements, how we understood, okay, in the same way we are going to understand this periodic law as well. Okay, so for example, we are like same starting from lithium, okay, moving to beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, okay, and then we are again back to sodium because it is having higher atomic number than neon. The next higher atomic number element after neon is sodium. Now sodium is placed here, see, below lithium, and the same thing goes on. We move on to magnesium, then aluminium, then silicon, then phosphorus, sulfur, chlorine, argon, and then again we come back to potassium by placing it below sodium, and the same story goes on. We find rubidium below potassium and cesium below rubidium. Okay, so now can you just see and try to understand? This group has the elements, okay, whose physical and chemical properties are similar. Okay, now after lithium, after a particular interval of atomic number, we are again finding an element which is having similar property to lithium. Same story goes on after sodium, and after a particular interval of atomic number, we are again finding an element which is having similar properties to that of the sodium and lithium. And then same story goes on after a particular interval, we again find rubidium which is having same property to that of the potassium, sodium, lithium, and so on, then cesium. So now you would have understood. See, the physical and chemical properties of elements, right, are found to be similar after particular intervals of their atomic numbers. Okay, now it would be very much clear for you. Now let's see the next question. Very interesting question. Why Moseley pushed out the atomic weight term and brought in the atomic number term in his periodic law, as well as used atomic numbers increasing order for arranging the elements in his periodic table. So, but for that, let's first study what actually atomic number means. Okay, so now let's see what actually atomic number means. It's very, very simple. Atomic number means the number of electrons in energy shells of an atom. Okay, so suppose let's take an example to understand this. If I'm having sodium atom, so suppose this is the sodium atom's nucleus. Okay, and then I'm drawing the energy shells. This is the first shell. I know sodium has second shell, and I know sodium has third shell as well. Okay, now in first shell, sodium has 2 electrons. So I'm just showing this E minus as electron. Then in second shell, sodium has 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. And in the third shell, it has 1 electron. So the number of electrons in the energy shells of an atom is the atomic number. So how many electrons are you able to see here? 1, 2, then 8 means 10, and 1, then 11. So there are total 11 electrons in the energy shells of sodium atom, which means sodium atom's atomic number is 11. Right? It's very clear. Now let's move to our question. What made Moseley to push out the atomic weight term and bring in atomic number term? Is he realized that atomic number is the fundamental property of the element. Okay. Now the question again arises, why on this earth atomic number is the fundamental property of the element? Because physical and chemical properties of the elements depends upon the number of electrons, okay, and their arrangement, how they are arranged. Okay, simply now you could just correlate this number of electrons term with atomic number, correct? What is actually atomic number? Number of electrons in the energy shells of an atom, and the physical and chemical properties of the elements are depending on the number of electrons. So this means that physical and chemical properties of the elements are depending on the atomic number. Now, if the physical and chemical properties are depending on the atomic number, see, the other physical and chemical properties of the element are depending on the atomic number, then this means that yes, atomic number is a basic or a fundamental property upon which other properties of the elements are depending. So I'm convinced that you would, so I'm sure that you would have been convinced right now that yes, why atomic number is a fundamental property of an element. Okay, and this thing made Moseley to push out the atomic weight term and bring in the atomic number term. Now, enough of Moseley, let's move ahead. Moseley gave us the modern periodic table, but right now the periodic table which we are using, the present version of the periodic table, is actually called as the long form of the modern periodic table, and this was given by a very, very famous scientist, very, very superb scientist Niels Bohr. Okay, now we have ended up the story of the development of periodic table. Now we are going to start with how, or we are going to start learning about actually about the modern periodic table. So now till this point we have just quickly gone through the story of development of periodic table, and yes, now we are actually going to study about the periodic table. So starting with the salient features of periodic table, but before that, just let's quickly see what a periodic table means. Okay, it's very, very simple. It's just a tabular arrangement of elements in horizontal rows, okay, like this, horizontal rows which are called as periods, and vertical columns which are called as groups, this, like this, vertical columns, okay, which are called as groups. But not simply a tabular arrangement of elements in rows or in periods and groups, but this tabular arrangement should also highlight regular trends in the properties of elements. Okay, now this regular trends in the properties of elements term you would understand in a better way when we would actually start learning about the periodic properties. Okay, now, but for now, let's see how the elements are arranged in the modern periodic table. Now you can see here in front of you, this is a modern periodic table, long form of the modern periodic table. Okay, now the arrangement is actually as same as that of the Mendeleev's periodic table. Okay, there are just few changes. Now I will tell you the few changes. First, let's see, the elements are arranged in the increasing order of their atomic number. This was the first change which was made. Okay, and just simply in horizontal rows, okay, and vertical columns. But the name of horizontal rows, which was series in Mendeleev's periodic table, now here we gave it as periods. Okay, we call the horizontal rows of elements as periods and the vertical columns as groups, same as that of the Mendeleev's periodic table. Okay, and this criteria was important criteria in the Mendeleev's periodic table was also this, okay, which is also followed in modern periodic table, which is actually what these elements are arranged in the horizontal rows called periods, vertical columns called groups, in such a way, this criteria, okay, in such a way that the elements having similar properties are placed in the same group. Okay, now here you can see, suppose for example we have taken this group. Okay, now you can see these elements are having similar properties. Okay, beryllium, magnesium, calcium, strontium, barium, radium. Okay, and they are placed in the same group. Now further we are going to study in detail about the periodic table now, but we are going to start first with groups. Okay, and then we are going to move ahead to periods. So yes, now we are going to start to learn about the groups of modern periodic table, but I would suggest you that you take a long big paper, okay, and you just draw the skeleton of the periodic table. Okay, just draw the skeleton, don't write the elements. Okay, whichever elements I am going to tell you, you just write that elements at that point of time, and in this entire process we are just going to learn, as well as we are going to make a chart so that you could remember it in a very simpler way. Okay, and you could also understand the entire periodic table. Okay, so now let's start with groups. First of all, how many groups are there in the periodic table? Just count the vertical columns and you would know. And yes, there are 18 groups, and these are numbered as, right, starting from this vertical column or this group as 1, then this is group 2, group 3, group 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and then 13th, 14th group, 15th group, 16th group, 17th group, and 18th group. Okay, now let's see actually each and every group. Okay, so starting from group 1, okay, these the elements which are placed in the group 1, okay, except hydrogen. I would write here, except hydrogen, all the elements of group 1, okay, which are this: lithium, sodium, potassium, rubidium, cesium, francium. Lithium, sodium, potassium, rubidium, cesium, francium. These elements are called as alkali metals. Now why they are called as alkali metals? It's very, very simple, okay, to remember, because these group 1 elements, except hydrogen, they react with water to form strong alkalis. That's it. So they are named as alkali metals. Okay, now you have to write all the elements of this group 1, okay, in your periodic table, because you have to remember all these elements. Okay, because we are going to learn about them at the end of the chapter in quite detail. So how to remember them? You would absolutely know the first element is hydrogen. Okay, then after that I would give you a simple trick. You can just remember in this way: LiNaC. Okay, lithium, sodium, potassium. See, lithium, sodium, potassium, and then you absolutely know our blood has RBCs. So RBCs, which means rubidium and cesium. See, rubidium and cesium, and then Fra. You just remember it as just Fra. So francium. Okay, now let's move on to the group 2. Now group 2, just like how group 1 is named, so group 2 is, like you can say, it's a younger brother of group 1. Okay, and it is named as alkaline earth metals. Okay, and yes, absolutely, you have to also remember the elements of group 2, which means you have to write in your periodic table right here. So the elements are beryllium, magnesium, calcium, strontium, barium, radium. Now how to remember this? Okay, now you would be knowing beryllium and magnesium, because I definitely know you would have remembered the elements up to atomic number 20, right, along with their symbols. But after that the real pain starts. Okay, you would be knowing the beryllium, magnesium, and then it would come calcium, but then after this strontium, barium, radium would be quite difficult. So what you can do is simply you just know beryllium and then magnesium comes. Okay, then you would just remember the Dobryner's triads. In the Dobryner triad, do you remember one triad which was calcium, strontium, barium, right? So see here, calcium, strontium, barium. Okay, so beryllium, magnesium, then Dobryner's triad, calcium, strontium, barium, and then barium has a rhyming tone with radium. So yes, it's radium. Now you would have now it would be easy for you to remember these elements. Okay, now moving to the next, group 3. Now don't worry, we are not going to see group 3 to group 12 each and every element, each and every group. We are just going to summarize the group 3 to group 12. Okay, all these elements which are present from group 3 to group 12 are called as transition elements. Okay, now what is special about them? These all elements are metals. Okay, first thing. And second thing is, all these elements means these elements have their two outermost shells incomplete. I just write here INC, incomplete. Okay, you just complete it. Okay, now we have reached till group 12, right? Then moving to group 13. Okay, so group 13 is named as boron family because its first element is boron. Similarly, group 14 is named as carbon family. Then group 15 is named as nitrogen family. Okay, and in the same way, group 16 is named as oxygen family. Okay, so you can write it here, write down. Okay, group 13, group 14, group 15, group 16. Now, oxygen family is also called as chalcogen. So I would write here group 16 is also called as chalcogens. Now this means, chalcogen terms means ore forming. Now why they are named as chalcogens? Because these elements, okay, the elements of these group 16, oxygen, sulfur, selenium and so on, they are found in the copper ores. Okay, so since they are found in the copper ores, they are forming copper ores, so therefore they are named as chalcogens. Okay, because chalcogens means ore forming. Now moving to group 17, yes, you have to remember the elements of these group. Okay, and it's very interesting, they all end with ene. Okay, so fluorine, chlorine, bromine, iodine, right, and astatine. Okay, till here if you remember, it's fine. Okay, no need to remember the last one as well, but these 5 elements you should remember and you have to write in your periodic table. So, and the name of this group, that is group 17, all these elements are termed as halogens. You would be knowing it. Okay, now why these are said as halogens? Because they are salt formers. Okay, these elements form salts. Okay, so till now we have reached till group 17. Now moving to the last group, group 18. Okay, now this group is also called as zero group. Okay, very interesting. And these zero group elements are also named as inert gases or noble gases. Okay, now it's very interesting. Question is why they are named as inert gases, okay, or noble gases. It's very simple. Okay, because these elements of group 18, okay, helium, neon, argon, krypton, xenon and radon. Okay, you can remember till here and you just remember like halogens. Okay, in one flow, like fluorine, chlorine, bromine, iodine in one flow ending with ene. So helium, neon, argon, krypton, xenon, radon, you just remember it as it is in a one go. Okay, now let's come back to the question why they are called as inert gases. Because they rarely react with the other elements of the periodic table. Okay, now why is it so? Okay, why these elements rarely react with other elements then? Because they have a very stable electronic configuration. Okay, and this means that the stable electronic configuration means their outermost shell, okay, the last shell is completely filled with electrons. So they absolutely feel no need to give electrons or to share electrons or to just accept electrons. Okay, so they are just very much happy with themselves, so they don't react with other elements, and therefore we have named them as inert gases which do not react. Okay, inert means which do not react. Okay, now let's move to the next part. Now we have seen all the 18 groups, but there are some groups which are like transition elements. From group 3 to group 12 they are named as transition elements. So this group 1, group 2 and 13, 14, 15, 16 and 17. Okay, all these groups, okay, are also named as or the elements of these groups are named as representative elements or normal elements or main group elements. Okay. Now their interesting characteristic is all the elements of these groups, okay, group 1, 2, 13, 14, 15, 16, 17 have their outermost shells incomplete. So you can just build a logic from here that yes, if their outermost shells are incomplete, yes, they are definitely going to react. Okay. Now let's see about the blocks. So this group 1 and group 2 elements are called as S block elements. Okay. These transition elements, okay, from group 3 to group 12 are called as D block elements. Okay. And from this here, from group 13 to group 18, okay, these elements are called as P block elements. Okay. Now the last block is F block, but we will just keep it aside. We will first learn about the periods and then we would move on to the F block. Okay. So the one more interesting thing about the groups is just we know that the group has, okay, every group has elements which are having similar property. So in the same way, okay, if we would see every group has elements having same number of electrons in their outermost shells. Okay. Now let's just understand this thing with an example. Okay. Just take an example of group 1. Okay. So in this we are having elements hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. So we would just see till potassium. Okay. And we would just get to know that yes, it's absolutely correct. So starting from hydrogen, it has only one shell and it has only one electron, right? Then lithium has 2 shells, electronic configuration is 2, 1. Sodium has 3 shells, electronic configuration is 2, 8, 1. Potassium has 4 shells, electronic configuration is 2, 8, 8, 1. Now you can see here the outermost shells are these shells and the electrons present in the outermost shells are given here. Okay. So all the elements, okay, these elements are of same group, and see here their outermost shells are having same number of electrons. Okay, so I know you're enjoying learning periodic table, and just now we have finished about the groups, learning about groups. Now we are going to move ahead on to the periods. Okay, now we are going to study in detail about the periods of modern periodic table. So starting from the first point, like we started with the groups, how many groups are there? So just in the same way, how many periods are there in the modern periodic table? So you can simply count and know, and yes, there are 7 periods. Okay, and they are numbered as simply just like groups: period 1, 2, 3, 4, 5, 6 and 7. Okay, so this is period number 1, this is period number 2, in this way, period number 3, period number 4 and so on, 5, 6, 7. Okay, now these periods have been given, means they have been classified into some types. Okay, there are very simple types based on the number of elements only. They are classified into types. Okay, so first let's see the number of elements in each period, and then you would understand the type as well. Okay, it would be easy for you to remember. Okay, so in the first period there are only 2 elements. You can see here hydrogen and helium. So we would write in front of the first period 2 elements. Okay, in second period there are 8 elements. Okay, from lithium to neon. So yes, 8 elements. Similarly in third period also you can see there are 8 elements. Okay, and in the same fashion in the fourth period, if you would count, you can see there are 18 elements. Fifth period also has 18 elements. Sixth has 32 and seventh has 32. So how you would remember? It's very easy, starting with 2, okay, which is very least number of elements present in the period, and then 8. So when it comes 8, again repeat it. So 8. So you already know second and third period has 8 elements. Okay, now then it comes 18. So the fifth will also have 18. Okay, the number would repeat once, and then 32, then it would again come 32. Okay, now based on this number of elements, the periods are classified into type. Simply first period, because it has only 2 elements, it is called as shortest period. Okay, then second and third period has 8 elements, therefore they are called as short periods. Okay, both of them. Fourth and fifth have 18 elements. Okay, so they are quite long, so therefore they are called as long and long periods, and the last two periods are the longest, right? So therefore they are called as longest periods, simply. Okay, now let's move on to the range of the atomic numbers in each period. This would help you actually very easily to determine which element is present where. Okay, so and you would also get a brief idea about the periodic table, how the elements are placed. So starting from hydrogen, now it has atomic number 1. So I will write here, yes, hydrogen atomic number 1. 2, there are only 2 elements, so atomic number 2 would come next. So helium atomic number 2. Okay, then from helium, now we have ended till helium, then we are going to come again this side. So it would be the atomic number 3 element. So it is lithium, right? Atomic number 3. I would write here lithium atomic number 3. Okay, and then now how you would know that what is the last element of that particular period? You just have to know the number of elements in that period. So we have reached second period, right? Now we know that there are 8 elements in the second period, including lithium, correct? So apart from lithium, there are going to be 7 elements. Okay, so 3 plus 7 would give us the last element's atomic number, which is 10, and here we go, neon 10. Then next element would be it would be 11, sodium, because it has atomic number 11. Okay, now in the same way, third period also has 8 elements. Okay, apart from sodium, there would be 7 elements. Okay, so we would just add 7 in 11, so 11 plus 7, 18. So we would get argon, right? Then same way we would come to potassium. Okay, having atomic number 19, because argon has 18, next would be 19, so 19 would come here. Okay, now in the same way, we know fourth period has 18 elements. Okay, including potassium, so excluding it would be 17. So we would just plus 17 in 19, so 19 plus 17 would be 19, 10, 29, and plus 7, 20, 36, right? So it would be 36 krypton. Okay, now in this way you would move ahead. You would get 37 is rubidium. Okay, rubidium 37, and then again you would add 17, just like period number 4. So 37 plus 17, 47 plus 7, 54. Okay, so you would get xenon 54. Then 55 would be cesium. Okay, now here there are 30, right? Now this period also has 8 elements. So if you would leave sodium, then there would be 7 more elements. So sodium 11 plus 7 would give us 19. Sorry, it has 8 elements. Okay, and including sodium, so we would just fix. So 87 plus 31, it would be 108, and the last 118, sorry, the last element of the periodic table, which is named as oganesson. Okay, it is very recently discovered element. So now in this way you actually know the group 1 elements. Okay, so it won't be difficult for you to remember the names of the elements. Okay, and you also know the names of the last group 18 elements. So it would be very easy for you to understand this, or it would be very easy trick for you to remember the range of the elements in the period. Okay, now one more thing, very much important thing, number of shells. So it's simply if an element is present in a particular period. Okay, suppose the period is period number 2, so it has exactly the same number of shells. Okay, means the period number is equals to number of shells. So if suppose I'm taking an example, we will just understand this by example. Suppose nitrogen. Okay, so it is placed in period number 2, we know that. So the number of shells in nitrogen would be 2, or vice versa. If you know in a particular element there are x, y, z or x number of shells, then this means that that particular element is placed in x period. Okay, so now from this logic, okay, we know that this is period 1, so all the elements in period 1 would have only 1 shell, correct? So here it would be 1. All the elements in period 2 would have 2 shells. Similarly, third period would have elements, okay, which are having 3 shells, 4 shells, 5 shells, 6 shells, and 7 shells. Okay, so now we have almost seen everything about the 7 periods, but one more interesting thing. Now see, these elements, okay, of period number 3, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, up to chlorine. Okay, these elements are called as typical elements. Okay, now why is this so? Because these elements summarize properties of respective groups. Now, what does this mean? If you would know the properties of these elements, okay, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, then you would actually know the summary of the property of a respective group. So suppose, for example, if you would know the property of sodium, then you would have a summary of the properties of group 1. Similarly, if you would know the properties of magnesium, you would have a summary of property of group 2. Okay, in this way. Now, I have told you that after studying periods, we are going to see F block, right? So now it's time to see F block. What are F block elements? It's very, very easy and it's very, very interesting as well. So see, there is quite a confusion among the students that actually lanthanum is included in F block elements. Like in the same way, actinum is also included in F block elements or not. Okay, so let me clear your confusion first. What are actually F block elements? F block elements are the 2 series elements, okay, or are the group of 14 elements, each placed in a group of 14 elements. Okay, now why are they called as so F block elements? We would learn it in the higher grade, but for now we call this 14 elements. Okay, now these are the 14 elements after lanthanum, therefore we call these also as lanthanoids, and these are the 14 elements after actinum, therefore we call them as actinoids. Okay, I will write it here: lanthanoids, actinoids. Okay, and these lanthanoids and actinoids are called as F block elements. Okay, so now your confusion would be clear. Lanthanum and actinum are not included in F block. Okay, apart from lanthanum, the 14 elements, and apart from actinum, the 14 elements are called as F block elements. They are respectively named as lanthanoids and actinoids. Why I told you right now? Because these elements are coming after lanthanum, these elements are coming after actinum. Okay, now lanthanoids start from cerium, okay, and they end to lutetium. So how you would remember this? See, before cerium it comes lanthanum, you know, and you would remember in this way: La to Lu. Okay, and after La it is Ce, cerium. Okay, now how you would remember the atomic number, the range of elements? It's very, very simple. See, lanthanoids, okay, here it comes here in 3rd group, so, and in 6th period. So now you would know that, see, this is the 6th period. Okay, now in 6th period, you know, it starts with cesium. Okay, and you know the atomic number as well, 55. You can calculate in the same way which I have told you how to find the range. Okay, so cesium is 55, and you know that from group 3 lanthanoid starts, means you know that from group 3, okay, lanthanum is there and lanthanoids are also placed in group 3. So group 1 would be 55, then group 2 would be 56, next element, and lanthanum would be 57. Okay, so if lanthanum is 57 atomic number, so cerium would have absolutely 58. Okay, and then from cerium to lutetium, now you know 14 elements after lanthanum. Okay, so from cerium to lutetium it is 14 elements total, including cerium. So excluding cerium it would be 13 elements. So you would just add 58 plus 13, so it would be 68, and then 3, 71. So lutetium's atomic number would be 71. So you have to just apply your brain, and you can use some tricks which are actually provided by the model periodic table itself, so that you could easily answer some questions which has no need of remembering the things. Okay, now, so you can minimize the things which you have to remember in short. Now similarly, actinoids also, it has the same case. First it would be actinum. Okay, from then after actinum it comes thorium, and then the last element is lawrencium. So you can just remember aclar, so you could remember the last element, and after actinum it comes thorium. You have to just remember in this way. Okay, now similarly, how we got the atomic number of cerium, we would also get the atomic number of thorium. Okay, so actinum has 89, okay, because 87 is francium. Okay, And we know that from 87 it would be 88 and then 89, group 3, 7th period. So actinum is 89, so thorium would be 90, and we would just add 13 elements in it because total including thorium there are 14 elements. So we would just add 13, so 19 plus 13 is 103. So actually you got the trick how to remember the range of F block elements. Okay, now these lanthanoids along with lanthanum and actinoids along with actinum, okay, are placed in the group 3, right? So why is this so? You would be knowing the answer, because they are having similar properties. So this can also be a question which can be asked. Okay, and another most important question is why these lanthanoids and actinoids or the F block elements are separately placed out of the periodic table. Why aren't they placed here itself? Okay, so firstly you can see that if I would place this 14 elements here, then this block, okay, this block of 2 periods would shift ahead. So what it would actually do? First thing, it would just distort the shape of periodic table, correct? Periodic table won't look in a symmetry just like it is looking right now. And secondly, which is the most important thing, we would lose our principle of classification. Loss of principle of classification. Now what is actually this? Our principle of classification is we are placing the elements having similar properties in the same groups, correct? Now if we would shift this entire 2 periods ahead, so now they are actually placed according to our principle of classification. See, hafnium and rutherfordium, okay, or these elements are along with the elements which are having similar properties. If we would shift them ahead, then the elements would not be along with the elements which are having similar properties. So yes, we would lose our principle of classification. So that's the reason why we place these F block elements apart from or separately from the periodic table. Moving to the next interesting thing. So far we have learned groups and periods, but one more interesting thing, how we can determine the period and the group, okay, means the period and the group number of a particular S block or a P block element. Okay, so for that, to determine the period number for all elements, okay, as I said, number of shells means the period number. Okay, so you would just find out the number of shells from the electronic configuration and then you would get the period number. So I will just here write number of shells, okay, is equals to period number for all the elements. But we are concerned with right now S and P block, no need to go into the D block and F block. So for all elements means it also is true for S block as well as P block. But now for group number, okay, now for S block elements, the number of electrons in the outermost shell is the group number directly. Okay, I would just write it here. For S block, so you would just find this with an example. We will just see an example to understand this. See, these are the two S block elements. Two groups comprise of S block elements. Okay, now suppose I took calcium. So its electronic configuration I know 2882. So here there are 4 shells. So I just figured out easily that it belongs to 4th period, but the last shell, the outermost shell, has 2 electrons, okay, and it is belonging to S block. So I would say that it belongs to group 2 because the group number is equals to the number of outermost is equals to the number of electrons in the outermost shell, okay, for S block elements. Now for P block elements, it's very easy. You have to just add 10, okay, in the number of electrons present in the outermost shell. So first you have to see the number of electrons present in the outermost shell and then just add 10 in it. Okay, so for example, if I took phosphorus, okay, so I know its electronic configuration is 285. Okay, so I would just easily figure out 3 shells, 3rd period, but 5 electrons in the outermost shell and it is belonging to P block element. So I would just add 10 in it. So what would happen? 10 plus 5 is 15, and yes, I got it belongs to 15th group of the periodic table. So you can just check, this is the 15th group and third period. Now let's quickly see which elements in the periodic table are metals, which are non-metals, and which are metalloids. Okay, now I'm going to tell you the trick as well to remember. See, all S block elements are metals, okay, except hydrogen. Okay, this is non-metal. Fine. Then all D block elements, as we know, they are metals. We have already studied while studying the groups. Okay. Then all F block elements as well are metals. Now, apart from S, D and F block, entire S, D and F block elements are metals. But in P block as well, there are some elements which are metals. Okay. So here you see this. All the elements which I have enclosed in this step-like box, these are metals. Now, why metalloids first? Because they are separating metals from non-metals in the periodic table. And here I have marked these metalloids in purple. So boron, silicon, germanium, arsenic, antimony, tellurium, polonium, all these are metalloids. Okay, it's better if you remember these names of metalloids, because they may be asked in your exams, or it's really good to know the names of the metalloids. Okay, there are quite a few, you can remember it. Okay, now moving on to the next, non-metals. Let's see which are non-metals. Now absolutely you could just guess, all the remaining ones are non-metals. So you can see here 0 group entire, and here this way, all these elements are non-metals. Okay, now let's see which all elements are solids, which are liquids, and which are gases. Okay, so you would think that out of 118 elements, now we have to remember which are solids, which are gases, and which are liquids. A tough job? No, actually, absolutely not. Okay, first of all, we are going to start with gases. Okay, and I'm also going to tell you some tricks, a simple trick. After that, you would definitely feel that, oh, it was very easy. Okay, so which all elements are gases? Very simple. First of all, we will start with the last group, and yes, the last group is entirely present in the gaseous state. Means the elements in the last group are present in the gaseous state. Okay, so helium, neon, argon, krypton, xenon, radon, all these elements are gases. You can see they are marked with light blue. Okay, and all those elements which are marked with light blue are gases. So you would have figured out it right now. Then now I'm just telling you the trick, okay, to remember. Then moving towards the previous group, okay, group 17. In group 17, we know they are halogens. So fluorine and chlorine exist in gaseous state, only the two. Okay, only two. And then moving again to the previous group, group 16, only one element. Okay, here there were two elements. Now the number reduced to only one. Only oxygen is in gaseous state. And then for group 15, only nitrogen is in the gaseous state. That's it. Oh, we are forgetting one more element which is very, very interesting, right? And it is, yeah, it's sitting on the top of the table. Hydrogen, yes, it also exists in the gaseous state. So we have covered which all elements are gases, right? Now let's see which all elements are liquids. So there are only two elements in the entire periodic table which are liquids, and you have figured it out, right? These with light pinkish color, they are marked with light pinkish color. First one is mercury. Let's see, it exists in liquid state, as you all be knowing that we were using the thermometers. Okay, right now we are not using, but we were using before some time or some time ago, the thermometers which were made of mercury, right? But we stopped. So from that you can remember, yes, mercury is liquid. And yeah, after chlorine, we know it comes bromine, and yes, bromine is a liquid. So only these two elements are liquid. Now it's very easy. Rest all the elements which you are able to see in the periodic table, apart from which we have seen as gases and liquids, rest all are, yes, absolutely, you're right, solids. Now I'm also going to tell you some trick to remember the solid elements as well. Okay, it's very easy. Apart from hydrogen, all S block elements are solids. You can see here, right? Apart from mercury, all D block elements are also solids. Okay, and yes, absolutely, all F block elements are also solids. Now coming to the P block, except the elements which are in gaseous state or in liquid state, rest all the elements are in the solid state. Simple. Now regarding the elements after actinoids, okay, after lawrencium, here you can see the element number 104 to 118. No need to stress out on these elements, okay, because these are recently discovered elements, so no need to remember the states of this element. You just remember the states apart from these elements. Whichever elements are there, you have to just remember it. And I have told you a trick. No need to remember the state of each and every element by seeing, oh, it is solid, solid, solid. A very simple trick would do work. So now our next topic is number of shells and valency. So actually what we are going to study in this topic, we are going to study the variations of number of shells, okay, across the period and down the group. This is across the period and this is down the group. And similarly, we are also going to study what is valency and how valency varies same across the period and down the group. So now let's start from number of shells. So down the group, we are going to see first down the group, the number of shells increases. Okay. Now, how you would remember this? Let's understand this by taking an example. Okay. Simply, if I take the example of group 18 or 0 group elements. Now, I know for this first period, the number of shell is 1. Why? Because the elements in the first period, because these elements are belonging to first period, okay, and I know the period number is equals to number of shells. So the number of shells in period for the elements in the period 1 is 1. Similarly, the number of shells for period number 2 would be 2. Same way, 3 would be 3, 4, number of shells would be 4. Then for xenon, number of shells would be 5. Radon, number of shells would be 6. And similarly, organosin, number of shells would be 7. Okay, because they are belonging to the respective period number. Now, I think you would have understood how the number of shells are increasing down a group. See, 1, 2, 3, 4, 5, 6, 7. Yes, number of shells are increasing as we move down the group. Simple. And then across the period, number of shells remains same. Now let's take an example of, suppose, period number 2. Okay. Now these elements, okay, of period number 2, all these elements have only 2 shells, right? How we came to know this? Because we know these elements belong to period number 2 and number of shells is same as that of the period number. So these elements having 2 shells. So when we are moving across the period, is there any change in the number of shells? No, it remains same. So now let's move ahead and see what valency means to us. So valency is simply combining capacity of an atom of an element. Okay. Now what does this combining capacity means? It's very simple. It's the capacity of an atom, okay, to donate electrons or share electrons or accept electrons. Why? Because in order to combine with other atom. Okay. Now, by understanding the combining capacity, we can actually say, right, that valency is quantitatively equal to the number of electrons, okay, an atom donates, accepts or shares, right? Yes. Now, let's see, valency, you would never see it as a negative number. Why is this so? Just now we studied that it is a combining capacity, right? So you only think logically how an atom can donate -1 electron, or how it can share -1 electrons, or how it can accept -1 electron, right? It is not possible. That's why valency can be seen as always. Now, let's see a simple trick to find the valency of an element. But before that, we have to first learn this thing, that valency depends on the number of electrons in the outermost shell, or we can just simplify it, depends on the number of valence electrons. Okay, Why? Because the number of electrons in the outermost shell, we called outermost shell as valence shell, and the electrons in the valence shell are called as valence electrons. So simply we can say valency depends on valence electrons, right? Very clear. Now, if the valence electrons in an atom of an element, okay, are 1, 2, 3 or 4, simply the valency is equals to 1, 2, 3 or 4, okay, which means simply the valency is equals to the number of valence electrons. If in an atom the valence electrons are 1, 2, 3 or 4, but if in an atom the valence electrons are 5, 6, 7 or 8, then the trick says that you just have to minus the valence electrons from 8, and whatever you get the answer, it is the valency of the element. Okay. Now in this case, see, if there are 5 valence electrons, then we would just minus the valence electrons, that is 5, from 8. So 8 minus 5 gives us 3. Similarly, 8 minus 6 will give us 2, 8 minus 7 will give us 1, and 8 minus 8 will give us 0. So this would be the respective valencies of the elements. Okay. Now, how this trick came? Let's quickly understand this, because if at all you would forget this, or you should know the concept behind this trick, I feel. Okay. It's very simple. You have already learned it. The octet concept, okay, is getting applied in this thing. So when an element has 1 electron in its valence shell, okay, for suppose example, we can take sodium, see here, 281. So what it feels that, yes, I want to reach the octet, okay, I want to make my outermost shell, which is having 8 electrons. This is called an octet, okay. So what it feels that, if I want to make my outermost shell having 8 electrons, then in this case, okay, I have to accept 7 electrons. Oh, sodium feels, no, I'm not going to do that, because it is very, very difficult for me. But instead, I can just lose this 1 electron so that my resulting outermost shell would have 8 electrons. Yes, sodium is smart. So it does the exact same thing. So it just donates this 1 electron. And yes, remember what we have learned, what actually valency is. Valency is equals to number of electrons an atom donates, right? So here it donates 1 electron, therefore valency is 1. Similarly, in case of 2 electrons in the valence shell, okay, for suppose example we take magnesium 282, it also feels the same way, therefore it also donates 2 electrons, therefore valency is 2. And in the case of 3 electrons in the valence shell, suppose example is aluminium 283, it also feels the same way, therefore it also donates 3 electrons, therefore valency is 3. Now comes the case in which valence shell has 4 electrons, and the example is, suppose, see, silicon, okay, 284. Now, in this case, silicon feels that, oh, now giving up 4 electrons as well as accepting 4 electrons is same to me. Then why not I should choose a simple way? I would just share my 4 electrons with the 4 electrons of other atom, so that this shell would have in all 8 electrons. And yes, silicon does that. Therefore, it shares 4 electrons. Therefore, valency is 4, because we learnt it that valency is also equals to the number of electron an atom shares. So here it shares 4 electrons, therefore valency is 4. Now coming back to this, if there are 5 electrons in the valence shell, okay, 2, 8, 5, and this is the electronic configuration of phosphorus. We have taken an example. Now in this case, phosphorus feels that, no, I am not going to donate my 5 electron at all. I am having 5 electron. So in order to complete the octet, it is easy for me to accept 3 electrons, right? And it does the same thing. Therefore, valency is 3, because we know valency is also equal to the number of electrons an atom accepts. And same story goes for sulfur, okay, 286, it also accepts. It also feels easier to accept 2 electron, therefore valency is 2. Again, chlorine 287, it feels easier to accept 1 electron instead of giving up 7 electrons, therefore the valency is 1. And yes, lastly the argon. Now you can see here it has 2, 8, 8. It doesn't has the need to either donate, either accept, or either share electrons, because it already has 8 electrons in its outermost shell. Its octet is complete. Therefore, its valency is 0 because it neither donates electron nor accepts nor shares electron. So now let's see the variation of valency, okay, down the group from top to bottom and across the period, that is from left to right. So first we are going to see the variation down the group, okay, from top to bottom. Now how valency varies? It's absolutely simple. It remains absolutely same, okay, no change in the valency. And why is this so and how is it happening? Let's see with an example. So I'm taking the example of this group, okay, group 2. Now if you would write the electronic configurations of all the elements of group 2, what you would find is all these elements, okay, are having 2 electrons in their valence shell, okay. The atoms of all these elements will be having 2 electrons in their valence shell, okay. Try writing the electronic configuration on your own, so you would figure out. Now what actually the point is, since the number of valence electrons is same, just now we studied that valency depends on number of valence electrons. And now let's try to find out the valencies, okay, of all these elements, okay. So we know that if the valence shell has 1, 2, 3 or 4 electrons, then number of valence electrons is equals to valency. So here valency is also 2 in all the cases, right, in case of all the elements in this group. Now you can see clearly that when we are moving from top to bottom, okay, that is down the group, valency absolutely remains the same. And why is this happening? Because number of valence electrons remains same, okay. Now let's see the variation of valency across the period, which means that from left to the right when we are moving across period, okay, how valency varies. So for that, let's take an example and you would automatically understand how is valency varying, okay. So for example, we are taking the period number 2 elements, okay, and we are now going to move across the period number 2 from left to right and see the variation. So for that, we have to first write the electronic configuration in order to find valency. So it is 2, 1 for lithium. We know for beryllium it is 2, 2. For boron it is 2, 3. Then for carbon 2, 4, nitrogen 2, 5, oxygen 2, 6, fluorine 2, 7, and neon 2, 8. Okay. Now from this it is very clear to us how many valence electrons are present in each of the atom of in each element's atom, okay. Now here in this case valence electron is 1, in case of beryllium it is 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and neon 8 valence electrons. Now from this we can calculate valency absolutely, because we know the trick number 1. If the valence electrons are 1, 2, 3, 4, valency is equal to valence electrons is equal to the number of valence electrons. So here valency would be 1, 2, 3 and 4. Okay, wait a minute. Then trick number 2. If valence electrons are 5, 6, 7, 8, we would just minus the valence electrons from 8. So 8 minus 5 would be 3, 8 minus 6 would be 2, 7 would be 1, and 8 minus 8 would be 0. Now it's pretty clear to you that how valency is varying. It's very simple. When we are starting from the left, okay, in a group, valency is increasing. See, 1 to 2, then 3, then 4. Okay, just keep a break. Here, after group 14, okay, this is group 13, we know, boron family, it is group 14. After group 14, valency again goes on decreasing, 3, 2, 1, 0, till we reach group 18. Okay, okay, now let's move on to the questions. But I would suggest you that what you do is you just pause the video, read the question, and then try to solve on your own. After solving the question, you can again resume and see whether your answer is right or wrong. If it is right, well and good, very good. And if it is wrong, you can know the right answer. So in this way, you would develop a logic, you would develop a sense of understanding whatever you have learned till right now, whether you are able to apply it or not. Okay, so your brain would start working. So now let's make our brain to work. Okay, so first, how does the electronic configuration in atoms change in a period from left to right, okay, and in a group from top to bottom. Okay. Now, for this, I have taken an example of a period, okay, to make you understand. See, period number 2, just now we have saw, and then the electronic configuration also I have written 2,1, 2,2 in case of beryllium, boron 2,3, carbon 2,4, nitrogen 2,5, oxygen 2,6, fluorine 2,7, and neon 2,8. Now, in this case, you can clearly see that number of shells, okay, are they changing? No, absolutely not. There are only 2 shells, okay. As we move across the period, okay, and we are seeing the variation in the electronic configuration, number of shells remains the same. So, number of shells is same, okay. For first, we are writing the answer for first. But what is changing? See, the number of valence electrons, yes, 1, 2, 3, 4, 5, 6, 7, 8. Number of valence electrons are changing. So, number of valence electrons are changing, okay. How they are changing? They are increasing, okay. So, this is your answer. Simply, now let's move to the second question. In a group from top to bottom, how electronic configuration changes? So, I have taken an example of a group, okay, group 1. So, now I have already written the electronic configurations, and I know you all have studied KLMN type of configuration, okay. So, hydrogen has 1, lithium has 2,1, sodium has 2,8,1, potassium has 2,8,8,1. Moving ahead, rubidium 2,8,18,1, okay, 2,8,18,8,1, and then cesium 2,8,18,18,8,1, okay. Now, after that, you can observe one thing. Yes, you know all this thing. You know this thing, that the number of electrons in the valence shell, okay, outermost shell, are same, right? Or the valence electrons are same in case of all these elements, okay. So, when we are moving from top to bottom in a group, how the electronic configuration is varying, okay, it is simply showing the same number of valence electrons. This is the first thing, okay. 2, number of shells I would tell you later. First, we have seen that number of valence electrons remains same, right? And now you have a look over the electronic configurations, you would definitely make out that number of shells are increasing. Here we are having 1 shell, 2 shell, 3 shell, 4 shells, 5 shells, and 6 shells, okay. So, number of shells here, they are increasing. So, without the help of periodic table, just like you would be solving the question in your exam or wherever you are, so in the same way I tried to solve the question so that it would be similar to you, right? You would feel the same sense. Okay, now moving to the next question. Name the first metals, second metalloids, and third non-metals in the first 20 elements. Okay, now no need to memorize the names of metals, metalloids, and non-metals till atomic number 20. We will just solve it by visualizing the periodic table which we have studied earlier, and just by knowing some basic facts, okay. Now, see what we have studied. We will first jot down the first 20 elements quickly, okay, how they are arranged in the periodic table. Now, I am also having a very blank paper like you. So, like you, I am going to solve this. So, first, let's start with hydrogen. It is, I am remembering, yes, hydrogen is at the cornermost in the top. Then in the right cornermost top, there is helium. This comprises of first period. First period is done. Okay. 1, 2, atomic number 2. We have to reach till 20 quickly. So, lithium, then beryllium. Okay. In period number 2, 3, 4. Okay. Atomic numbers. Then I'm having a gap, I know. And then I'm going to start with, yes, next element is boron, 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, and neon, yes, 10 below helium. Now, next, moving ahead, sodium 11, magnesium 12. Okay, I'm writing the atomic numbers. Then aluminium 13, silicon 14, phosphorus 15, sulfur 16, chlorine 17, argon 18, and then next is potassium 19 and calcium 20. Yes, now we would figure out which are metals, metalloids, and non-metals. So, using the logic and using the visualizing the periodic table, okay, and we have learned it as well, how to remember which are metals, which are metalloids, and which are non-metals. So starting with metalloids, okay, there were like a borderline elements. I have told you to remember it, okay. They were marked in something like green, okay. So now here it goes. These are the metalloids, right? This was the border, boron, silicon, okay. Then we would move to arsenic, antimony, right? In this way. So boron and silicon, we got our metalloids, okay. So metalloids are boron and silicon, okay. We will write the metals here and the non-metals here, okay. Now we will go entirely through the 20 elements and we will find it, okay. Now first, hydrogen, yes, it is a non-metal, we learned it, okay. So yes, we will place it in non-metals group. Okay, I will just make circle for the non-metals. Then helium, absolutely, all the group 18 are non-metals, we know. Or we know that after this border line, okay, after this border line, everything, all the elements are non-metals. So here, absolutely, helium is non-metal. So helium. Then before the border line, all the elements are metals, we studied. So lithium and beryllium are metals. Lithium, beryllium, okay. Alkali metals, lithium, and alkaline earth metals, beryllium, the name suggests, okay. Then carbon, nitrogen, oxygen, fluorine, neon, all the non-metals, okay. So carbon, nitrogen, oxygen, fluorine, neon, yes. Then again moving to here, sodium, magnesium, again sodium alkali metal, magnesium alkaline earth metal, and also they are to the left of the border line. So we know to the left of the border line all are metals. So yes, sodium, magnesium, metal. So sodium, magnesium, metal. Aluminium would also be the metal because it is to the left of the border line, okay. So aluminium. Then after that, phosphorus, sulfur, chlorine, argon, all non-metals. Phosphorus, sulfur, chlorine, argon, non-metals. And same way, potassium to the left of the border line, metal, calcium, metal. So potassium, metal, calcium, metal. See, we solved the question without remembering any element which is metal, which is non-metal, and which is metalloid. So going to the next question, name the type of elements which have their one electron short of octet, two electrons in the outermost orbit. So let's start with the first one, okay. One electron short of octet. Now in order to answer these two questions, it's very simple. You have to just know the electronic configurations, means till first 10 elements, okay. If you know this much only, then also you can answer this question, okay. Now I know you know the electronic configuration of many elements, okay. How to write the electronic configuration, you already know. So just apply the concept of electronic configuration till first 10 elements. So what it is saying, one electron short of octet. So it means that 7 electrons, right? Octet means 8 electrons, 1 electron short means 7 electrons. So 7 electrons are in the outermost orbit. So first 10 elements, okay, which element has 7 electrons in the outermost orbit? Think. Fluorine, yes, 2,7. Its electronic configuration is 2,7, and yes, it has 7 electrons in the outermost orbit. Now pay attention, what they have asked, name the type of elements which have. So they haven't asked us the name of element which has 1 electron short of octet, type of element. Now we have just now discovered, yes, fluorine has 7 electrons in the outermost orbit, but we know that if the other elements in the same group, okay, not if, but we know that the other elements in the same group, okay, of fluorine will also have 7 electrons in the outermost orbit. Yes, because we know that in a same group, all the elements are having same number of valence electrons in their, or same number of valence electrons, okay. Now, so just like fluorine, chlorine will also have 7 electrons, bromine will also have 7 electrons, iodine will also have 7 electrons. Now, what does this group of elements, we have studied it earlier, what is the name of this group of elements, right? Group 17, but yes, it has a particular name, halogens. Yes, absolutely. So we got the answer, okay. So in this way you have to solve such questions. Now next is 2 electrons in the outermost orbit. Now you try to solve it, okay. Now see, 2 electrons in the outermost orbit. Now try to find which element is having 2 electrons in the outermost orbit till atomic number 10. Yes, you're right, beryllium, 2,2, right? Electronic configuration, beryllium, atomic number 4, 2,2. So now like beryllium, all the elements in the group of beryllium would have 2 electrons in their outermost orbit, same like the halogens, right? Same logic in the case of halogens we applied, we are also going to apply the same logic. We know that the elements in the same group are having same number of valence electrons. So yes, beryllium, magnesium, then calcium, strontium, barium, radium, all are going to have 2 electrons in the outermost orbit. And what we call this type of elements? Group 2 elements are called as, we have already learned, alkaline earth metals. So yes, we got our 2 answers. This is the second answer. Okay, so next one is, an element has 2 electrons in its nth shell. Okay, so we know the electronic configuration pattern. We arrange the elements in this shells, K, L, M, N, O, P, and all, and so on. Okay, so now they are saying us that nth shell has 2 electrons. So this N shell, okay, N shell has 2 electrons. Sorry, it's not nth, it's N shell. Now let's try to figure out which element it is. Okay, what they have asked us first is, what is its atomic number? This is our first question. So we have to figure out the atomic number. Now in this case, we will just apply a simple logic. See, there are 4 shells. They have said us that 2 electrons in the N shell. Okay, so it's very clear that beyond N there would be no shell. Okay, means beyond N there would be, beyond N shell, okay, suppose O shell. The O shell has no electrons. So this means that the N shell is the outermost shell. Now the outermost shell has 2 electrons, and this means that shell number 1, shell number 2, shell number 3, shell number 4. So the element has 4 shells. We got a clue. Now if it has a 4 shells, this means that the element belongs to 4th period. Absolutely correct. You are going right. Okay, because we know that period number is equals to number of shells. So number of shells is 4. So period number should be 4 of that element. Now try to think, try the trial and error method. So let's start, which elements are there in the 4th period. Okay, starting from potassium, right? The 4th period has potassium because we know the first group elements, right? Hydrogen, lithium, sodium, potassium. This is the period number 1, 2, 3, and yes, 4. So potassium's electronic configuration is 2, 8, 8, 1. Okay, then next it is not having 1. Oh, the next element has 2, right? Calcium has the electronic configuration 2, 8, 8, 2, and yes, this is the N shell which is having 2 electrons, and we got our answer. Yes, the element is calcium, but our answer is, what is the atomic number? And now we know that atomic number of calcium is 20. You can also know this by calculating the number of electrons. So it is 2 plus 8, 10, 18, 20. Simple. So we got the atomic number 20, correct? Then state its position in the periodic table. Now see here, we know that it belongs to 4th period. So yes, for determining the position, I have taught you that we just need to tell in which period it belongs, in which group it belongs. Okay, and then that's it. So 4th period, it belongs to 4th period. Yes, so 4th period. And now group. So you can clearly see here, it is calcium and it has 2 electrons in its N shell. Now we have also studied that in case of S block elements, okay, the electrons which are present in the outermost shell is equals to the group number. And we also know, I have told you to learn the group 2 elements, and yes, it is a group 2 element, right? And you can cross check. See, it has 2 electrons in its last shell, and I have told you that if the element belongs to S block, then the number of electrons in its last shell would be equal to the group number. And yes, we know calcium is belonging to group 2. So yes, our logic is correct. So we have reconfirmed, and then yes, we got the answer. It belongs to group 2. Okay, next, is it a metal or a non-metal? Think clearly. We know that before the border line, all are metals except hydrogen. So yes, absolutely, this is a metal, and we also know its name. It belongs to the group 2, which is called as alkaline earth metals, right? Okay, so next is state the name assigned to this group. Just now I told alkaline earth metals. Okay, you can write it in the full form. And then next is, what is the valency of this element? Very, very simple. Last shell has 2 electrons, which means valence electrons are how many? 2. So valency would be equal to the number of valence electrons, in this case according to our trick. So therefore, valency is equals to number of valence electrons, which means valency is equals to. Moving to the next question. Fifth, name the element in period 3 which does not form oxide. Okay, so we know the period 3 elements. Which are they? Sodium, magnesium, right? Aluminium, silicon, phosphorus, sulfur, chlorine, argon. Okay, you have to remember the elements compulsorily till atomic number 20. And yes, by logic you know that yes, hydrogen, then lithium, and then sodium. So third period starts from sodium, and after sodium you know the name of elements: magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. So these are the third period elements. Now out of this, think logically, which element does not form oxide? Which element will not combine with oxygen? Okay, got the answer? Yes. See, all these elements, okay, out of all these elements, we can definitely say that yes, this element will not react with oxygen, because we know that we call the elements in these group as inert gas elements, because they hardly react with other elements. So yes, we got our answer. Definitely we can write argon. Okay, then next, the element out of lower nuclear charge, the element of lower nuclear charge out of beryllium and magnesium. Okay, now first of all, you know all what the nuclear charge means. Nuclear charge means number of protons. Okay, we all know this. Now, number of protons is also equals to the atomic number. We also know this thing. Now just we have to figure out which of the element is having a lower atomic number. The element which is having a lower atomic number will have lesser number of protons and will have lower nuclear charge. It's very, very simple. So out of beryllium and magnesium, we know that after beryllium, magnesium comes. And yes, beryllium has 4 atomic number 4, magnesium has 12. We all have learned till the we all have learned the elements till 20. So it's very simple for us. So yes, beryllium has lesser atomic number, which means that it has less number of protons, which means that it will have less nuclear charge than the magnesium. So yes, our answer is. Now moving to the last question. Okay, but pay more attention because this was asked in your examinations in 2017. Okay, so match the atomic number 19, 15, 8, 4 and 2 with each of the following. Okay, so they have given us 5 questions and 5 atomic numbers. So it's very, very clear first of all that each question has only one answer. Simple. Now first is a metal of valency 1. Okay, now we have to just apply our brains and figure out which of this atomic number would satisfy this condition. So if the element is having valency 1, then just think how many number of valence electrons it may have. Okay, it's very simple. It can be 1. Okay, because if it has 1 valence electron, then valency can also be 1. Okay, but the second case is it can also have 7 valence electrons, because in this case as well valency is 1. Okay, how here is valency 1? We know that in case of 1, 2, 3, 4, number of valence electrons are, if 1, 2, 3, 4, then valency is equals to number of valence electrons. If number of valence electrons are 5, 6, 7, 8, then valency is equals to 8 minus number of valence electrons. So here see 8 minus 7, it's 1. So in these both cases, okay, if valence electrons are 1 or 7, we can have valency as 1. So now we have to figure out from all these atomic numbers that which of these atomic number or which of the element having this atomic number, okay, is having either 1 or 7 valence electrons. It's very, very simple. Now we have to just go through the trial and error method. So let's start with 19. Okay, let's see how lucky we are when we are getting the answer. So what we have to do is actually we have to just pick up the atomic number and try to write its electronic configuration simply, so we can find out how many number of electrons are present in its valence shell. If it is 1 or 7, we have got our answer. Okay, so let's start 19. So I can write here first in first shell, K shell I am putting 2, then 8, L shell, M shell I am putting again 8, because I am having 9 more electrons after 10. Okay, so I have put 8 electrons here in L shell, and in N shell I am putting 1 electron. Okay, so total is 19. Oh yes, we found out an atomic number or an element having atomic number which is having valence electron 1 or 7. Okay, now it's very clear, 5 atomic numbers, 5 questions. So yes, one right answer would be there for each of the question. Okay, so yes, we have found out one valence electrons in case of this atomic number 19. So it is satisfying our first condition. Now wait a minute, just don't write 19 here, because we have to also satisfy the second condition. Is it a metal? Just let's cross check. So 19 atomic number is of potassium, right? And yes, absolutely, it's a metal. So yes, it has satisfied our both the conditions. So answer is 19. Then a solid non-metal of period 3. So 3 things we have to just cross check about the atomic number. First is period 3. Okay, let's start with it. So 15842. Now out of this, you can just think logically. Period 3 starts from sodium. Okay, how I'm knowing this? Just I'm having the knowledge of periodic table. Okay, I'm visualizing the periodic table. I know hydrogen, then lithium, and then sodium. So third period starts from sodium. Sodium is atomic number 11. So third period would have elements which are having atomic number more than 11. So it's very, very clear here that these 3 cannot be our answers. So simply 15 is our answer. So in this way also you can think quickly. Okay, but just try to confirm all the other clues as well. Okay, don't just be in a hurry to write the answer. Okay, so yes, now let's check whether all the other 2 clues given to us are right or wrong. Okay, means are matching or not. So it should be a non-metal as well. Okay, along with an element of a period 3. So let's check. Our 15 atomic number element is phosphorus, and yes, it is a non-metal, absolutely, because we have studied that after a borderline element, okay, rest all the elements towards the right are non-metals. So simply see silicon and then phosphorus. So silicon is a borderline element, you can remember. So after silicon, everything would be non-metal. So yes, phosphorus is a non-metal. And then the next third clue or third condition is it should be a solid. So just remember, try to remember, we have studied that all the group 18 elements were gases. Okay, then in group 17 fluorine and chlorine were gases. Then in group 16 only oxygen was gas, and in group 15 only nitrogen should be the gas. Rest all were solids. So yes, absolutely, here we can see nitrogen and then phosphorus. Okay, in the nitrogen group, nitrogen family. So phosphorus is solid. Okay, because except nitrogen all are solids. So phosphorus is absolutely solid. That's it. Okay, or else you can also remember in this way. You may be knowing the elements. You would be remembering all the elements which are in gaseous state and liquid state. So rest all are solids. So phosphorus is also getting into this thing. Okay, you can also figure out in this way as well. Okay, now, so yes, we have figured out that all the 3 clues are correct. So phosphorus is our answer. Then a rare gas. Now it's very, very simple. We have gone through these 2. Okay, these 2 are done, atomic numbers. Now last remaining are 8, 4 and 2. A rare gas. Okay, so out of this we know 8 atomic number is of oxygen, right? 4 atomic number is of beryllium and 2 is of helium. So out of this, oxygen and helium are gases, and absolutely you would have guessed helium is a rare gas. Oxygen is absolutely not a rare gas. We breathe in this gas so much and it is absolutely very abundant. Okay, so helium is our answer. Helium is a rare gas. So atomic number 2. Okay, next, now remaining 8 and 4, out of this a gaseous element with valency 2. You would have figured out. Yes, you're right. The answer is 8, oxygen. But yes, let's check the next condition as well. It should be having valency 2. So oxygen's atomic number is 8, electronic configuration is 2, 6. Valence electrons are 6. So we can figure out the valency as well, right? 8 minus 6 by applying the trick B, okay, which we have studied. So 8 minus 6 is 2. So valency is 2. Yes, it's correct. Okay, so both of the conditions are followed, gaseous element as well as valency 2. Our answer is 8. Okay, this follows our both of the conditions. So answer is 8. Then lastly, what is remaining? The 4. So answer would be 4, but let's also reconfirm the conditions as well. So an element of group 2. Now we know beryllium, the first element of group 2, right? It starts from beryllium, then magnesium, then calcium, then strontium, barium, radium. Okay, so yes, it is an element of group 2. It is satisfying this condition, element of group 2, and yes, our right answer is. So we have reached the end of this video, and I hope you all have enjoyed learning with me. But please do comment and tell me whether you have understood whatever things we have learned so far. And you all know, LearnoHub matlab free hai par best hai. So stay tuned. We will meet again in the next video. Till then, bye bye and have a great day.